Now we're going to talk about priority queues. It's common to implement a priority queue using a heap. I made another video talking about heaps and how we insert and remove elements from the heap. If you haven't seen that already, you should probably watch that. All right? Well, let's talk about the general idea of a queue first. And we'll see why heaps are used for priority queues. So you may recall that a queue is a first in, first out data structure. Okay? It's like the line that you have maybe at a store. So here's the line that people get into, and they're coming in from this end. So Bob shows up first, so he's at the beginning of the line. He's followed by Mary, who's followed by Ralph, who's followed by Susan, and so forth. And because it's first in, first out, that means Bob would be processed first, Mary's processed second, Ralph third, Susan fourth. So in a sense, there are priorities here in terms of how people are processed, but the priority is tied directly to who got here first, or maybe who's been waiting the longest, or something like that, which is why we process Bob, then Mary, then Ralph, and Susan. But what if instead somebody shows up in the line and they're considered a more important person? Okay, so Marcus shows up, and Marcus talks to Susan. He says, oh, well, it turns out I'm really more important than you. So Marcus really should swap places with Susan. And then he talks to Ralph and says, oh, well, I'm really more important than you, so I should swap places with you. And he talks to Mary, and he talks to Bob. And so Marcus moves up to the front because he didn't realize he was more important than all of these people until he talked to each one. Well, this means he had to have a conversation with Susan, then Ralph, then Mary, then Bob. So if there were 1,000 people in line, and Marcus really should have been at the beginning, he has to interact with all 1,000 people. So he has to interact with the N people ahead of him. And something similar would happen if one of these people suddenly realized they have to move up in line, right? If Ralph suddenly realizes he's more important than Bob or Mary, now he has to interact with each of them. So the question is it possible to do this in a more efficient manner? Because there are situations where each thing or each person that shows up has its own distinct priority that is independent of what time they showed up. Okay? And so for this, we're going to use a heap. And why is that? Well, remember that a heap is represented as a complete binary tree. So maybe we have this. And let's say right here, this is the existing tree. Well, in the case of a heap, when we insert something, it would go in the next available spot. But what's the worst case scenario? Like if this was the Marcus of this example, and he really should move up to the top because he's more important than all these others. Well, we did have 7 nodes, and now we have an 8th node, right? So now we have 8 nodes, which is 2 cubed nodes. So what's the relationship between this and the height of the tree above this? Well, if we have the log base 2 of 2 cubed, this is 2 to what power is equal to 2 to the cubed, which is 3, which is the height, or at least the height above this last layer. So instead of having to talk to all 7 people, he at most has to talk with 3 people. And obviously, as the tree gets taller and taller, this becomes more and more efficient. Okay? So this is the reason why we would say this has big O, and normally log base 2 is written like this. There's n nodes, log n. This is the complexity of the heap for inserting something and having it move to its correct position. Okay, this is the worst case, right? It may stay here, but in worst case, it moves up. So what if really I had 8 nodes already and added a 9th? Well, the log of 9 is still approximately 3. The log of 10 is roughly 3. It's only after this is completely full in which I would have 15 total nodes. I add the 16th. Well, the log of 2 to the 4th is just 4. So all these values are really going to be in the range of 3 to 4. So we say it's log of n. Right? So what happens? We may have a tree like this where the numbers that I'm storing are the priorities of the things that are added to the tree. So say I have 20 here, and maybe I had 10 and 15, and this is 3, and this is 2, and maybe that's 12 and 14, and maybe that's 1. Okay? So remember, what I'm using here is a max heap, which says if we look at any node, its value is greater than or equal to its child nodes. So 20 is greater than or equal to 10, and it's also greater than or equal to 15. 10 is greater than or equal to 3, 10 is greater than 2, and so forth. So because 10 is greater than 3, then 20 has to also be greater than 3 since it's greater than 10. All right? So let's say what happens is we add something new, which would go in the last position, and its value is 18. These are the priorities. So now we need to check how this priority fits in relative to the others. We need to check the max heap property. And see if we still maintain that. We don't at this point. So what would happen is we will compare 18 to 3. Okay. And I'm just going to do it in place here. So these would swap. This would be 3. Now this would be 18. Compare 18 to 10. They're not in the correct order. So 10 goes here and the 18 goes here. Compare 18 to 20. This is correct. So the final version would be this. Right. And that's from adding something else. Now, in many cases, what would happen is we need to also just pick off whatever has the current greatest priority, which we know, if we're maintaining the max heap property, will be the top node. So that has a performance, a big O of 1, because we only have to look at this one spot and get its value. So what would happen then? Well, we're removing a node. So going back to what I had here, we're going to replace it with the last node. And then we need to fix the tree if necessary. So if I copy that down, that means we put the 3 at the top. 18, 10, 1, 2, 15, 12, and 14. So 3 is supposed to be bigger than 18 and 15, but it's not. So one of these needs to move up. Because I'm using a max heap, I'm going to use the 18 since it's also bigger than 15. So this becomes 18, 3, 15, 10, 2, 1, 12, 14. Check now the 3 relative to these. It's bigger than 2, but not bigger than 10. So 18, 10, 15 there. This would be the 3, the 1, the 2, the 12, and the 14, right? Another thing that can happen with a priority queue is that something changes its priority. One of the applications that this would get used for would be situations where you're concerned about lots of new things showing up with much higher priority, and then something basically just gets forgotten. Not in the strictest sense, but what happens is it just keeps waiting because it's waiting to take its turn, but things that are considered higher priority just keep showing up. And so what could happen is the priorities of the existing things increment over time, such that maybe like 14 becomes 15, then it becomes 16, it becomes 17. So that way eventually it's going to get its turn, even though things that were bigger than 14 to begin with keep showing up. So let's say that 12 changed its priority. So now 12 becomes 30. So what do we need to do? Well, because it's bigger than 15, it needs to move up. So what would happen in this case is now I still had, this is 18 at the top. So I have 18 here, 10. The 30 and the 15 need to swap. So this becomes 30, 15, 14, 3, 2, 1. Then you check 30 to 18. That needs to be fixed. So we have 30, 10, 18, 15, here 14, 3, 2, and 1. And 30 is at the top, so it can't move anymore. There's two other possibilities, though. What if we had this right here, and 18 changed to 20? Well, 20 is still less than 30, and it's also greater than 15 and 14, so nothing needs to be done to fix the tree. It's still in the proper arrangement, okay? Now, priorities could go up, but then conceivably they could go down. So in that case, what would happen? Let's say we have 10. We'll use this existing tree. We'll use the 20 that was here. What if the 10 becomes 5? Or, well, actually, that would still be greater than these. Let's say it becomes 1 as well. Okay? So let's say 10. We'll start with this tree. Let's rewrite it here. So we have 30, 10, 3, 1. There's nothing here yet. 2, 20, 15, and 14. And the 10 becomes 1. It's been reduced in priority for whatever reason. What happens? Well, it's still less than 30, so it's fine with regard to that, but this puts it bigger than 3 and 2. So what happens? Well, 3 is the bigger of 3 and 2, so 3 is the one that moves up. So I'd have 30 here, 3, 20, there became a 1, there became a 1, there's a 2, 15, 14. It's fine relative to where it's at, because remember, it has to be greater than or equal to its children. Well, 1 is greater than or equal to 1. If instead it had been 0, then these two would need to swap as well. So if this had been 0 here, then what I would have here would be 0. 0 is not in the right position relative to 1. So I would need to swap them. I'd have 30, 3, 20, 1, 2, 0, and then the 15 and 14. So that's how a priority queue works. We can add brand new things that have their own priorities, which is what I showed earlier. Right here, it goes at the end just like any other insertion, and then you fix the tree as necessary. We also can change priorities of existing nodes, and the three possibilities there are: something needs to move up because now its priority is greater than its parent. It moves down because its priority is lower than at least one of its children. Or its priority changes, but it's still smaller than a parent, but greater than most of its children, and then nothing happens to it. So that's a priority queue implemented using a heap in this case. But you could implement it using other things as well. It's just for the reasons I gave you here, this performance, that it's often used for that. Okay, so that's a priority queue.